Okay, so number 54, a large box of mass capital M is moving on a horizontal surface at speed, velocity initial. A small box of mass lowercase m sits on top of the large box. The coefficients of static and kinetic friction between the two boxes are such and such, respectively. Find an expression for the shortest distance, d minimum, in which the large box can stop without the small box slipping. Alright, so let's just dive right into this. So what the situation looks like, we'll just move this down a little bit, is a bit like this. So we have this big box and we have this little box sitting on top of it, and this is moving this way at some value v initial. The mass of small box is little m, mass of big box is big M, and the free body diagram of little m looks a bit like this. We have the force of gravity, the normal. This should be swapped, actually. The force of gravity is going down and the normal force is going up. The static friction and the kinetic friction this way. And we know that the static friction is equal to the static friction coefficient multiplied by the mass times gravity, which is equal to the force of N, because we know that the force of N and the force of G are equal because these boxes are not moving in any vertical direction. So we need to find an equation for d minimum so that the static friction and the kinetic friction are equal, so the small box doesn't slide with respect to the big box. And we need to make sure that these values don't change depending on the velocity. So we're going to use kinematics here. So we have this equation here, and the final velocity is going to be equal to 0 because that's when the box stops, and so there's going to be no velocity at that moment. And so we have this here. And since, pardon me, we're trying to find d minimum, we need to define the acceleration in terms of what we are given. And here's a short list of what we are given. So Newton's second law, if you recall, is the force is equal to the mass times the acceleration. And we have this static friction value here. We're going to put that equal to the mass times acceleration. And we know that the static friction force is equal to the static friction coefficient times mass times gravity. So we're going to plug that in for here. And then we're going to solve for A. So we're going to divide by m, and the mass is going to cancel out. So we're going to end up with the acceleration is equal to the static coefficient multiplied by gravity. And so what we're going to do, we're going to plug that in to our equation from above here, and we're going to solve for d minimum. And we're going to get d minimum is equal to the initial velocity squared divided by 2 times gravity times the static friction coefficient. What did we practice today in terms of what we're learning is just kinematics, effective use of free body diagrams, and linear motion. We've been practicing this for a couple weeks now in terms of like the kinematics and linear motion. We're just slowly getting more complicated, and we've been messing around with free body diagrams for also a couple weeks. And so today was just a bit of practice for this. All right, awesome. Thank you very much, and I hope you have a lovely day.